So for the vacancy, it's a negative change in volume, and our pressure, because this is going to be negative here, it'll be positive, so we get a net minus sign in this term. So that means, again, this standard enthalpy of formation will be reduced. So if we're reducing essentially the enthalpy of formation, they're going to want to form here. So vacancies are going to want to flood in this region. They're not going to want to go into this region. Why is that? Because my stress terms are all positive. So a negative times a negative change in volume, that's going to be a positive, so that's actually not going to increase. For the interstitials, however, now we have a positive change in the vacancies. So now if I look here, positive change in volume, this is also positive, so the interstitials are not going to want to form in here, so they're not going to go into where this top region here, they're going to want to form right below here. So interstitials, when I look at my edge dislocation, the vacancies are going to want to flow to the top, my interstitials are going to want to flow right to the bottom. Excellent. So I have a left-hand screw with the tangent vector line with 2 axes. What vacancies will prefer to form around the defect? Or will vacancies perform around a defect? What if it's right-hand screw? Again, for screw dislocations, the answer is there is no, and actually we can look at that right here. For a screw dislocation, we don't have essentially stress components that are normal. So for a screw defect, oops, way over here, way down, I only have shear stresses. So I'm not going to have any, all this will always be 0. So screw defects will not interact with those point defects. Fantastic. So I have an edge dislocation with a tangent vector line with the 2 axis, and Berger's vector lies in the 1-2 plane. I apply a 3D complex stress state to the system. Which stresses result in climb? Which stresses will contribute to glide? How the answer change if I have the defects below? So edge dislocation. So I have a tangent vector in the 2 axis. So for the first problem, I have 0 aligned with the 2 axis, 1, 0. So my Berger's vector lies in the 1-2 plane. So I'm going to say that it is going to be, again, in the 1, 0, 0. It could be negative as well. I apply a complex stress state, meaning that I have sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 1, 2, sigma 2, 2, sigma 2, 3, sigma 1, 3, sigma 2, 3, sigma 3, 3. So that is my complex stress state. So I am asked which stresses are going to result in climb, which stresses will result in glide. So effectively, I have to look and calculate what is my Peach-Kohler force acting on this. So my force will essentially just be the stress that's applied, which is this stress in the system, dot with my Berger's vector, and then I'm going to cross product with the tangent vector. So let's go ahead, let's calculate that. So I am going to give me, so actually here, this is my generic stress. So this is my generic stress state. Here, I'm going to say that my T, actually let's just call this T1. Actually, we'll just call this TA prior. 0, 0, 0, 1, 0, just like we defined here. Actually, let's go ahead. Let's not do that. So what we're going to do, we can zoom out a little bit. And yeah, let's move that there. Isn't it fun with this? So much easier, right? Except not that one. I want this one. All right. So I've got my tangent vector, TA, 0, 1, 0. I've got my, because it's an edge dislocation, so it needs to be perpendicular. So again, my BA, it could be 1 minus 1, but I'm just going to go 0, 0. And so now my F of my general stress on A is just going to be, again, so sig, where this is my generic sigma, sig dot my Berger's vector, BA, and then I'm going to do cross with my TA, and voila. So this is a vector. So this is along the 1 direction. This is along the 2 direction and then the 3 direction. So in the glide plane where we're moving, this would be essentially the stress that corresponds to glide. Climb would be in the opposite direction, perpendicular, so it would be this sigma 1, 1. Fantastic. How would the answer change if I had the other defects? So now let's go to these guys. So let's do the same problem. And then actually, let's go ahead. I'll call it F1. So we have T1, which is minus 1 here. We have a 0. So we have a B1, which is a 0, 0. What type of defect is this? Well, it's an edge defect because it's 0. So T1, and then let's do T2 right now. And then we know that that one is a right screw. So F1, let's do F2 as well. Sig dot B2, T2, B1, T1. So here and here. So how the answers change, again, what is our glide plane? So if we want to figure out our glide plane, we actually have to find the normal. So I need to do the cross. My normal will just be T1 cross B1. So this would be my glide plane. So my sig 3, 3 would be glide. The sig minus 2, 3 would be in my climb. If I look at this one, T2, B2, because again, I'm using this relationship that my normal is equal to basically T cross B over magnitude of T cross B. So this gives me my normal. The normal to the plane is actually the plane I'm in, so then I can see which is the direction of movement in the plane and which one is not. So let's go back over here, and I look at T cross B. Ooh, that's a, why do I get this? Because this is a, again, for screws, I don't know what the glide plane is. So I get this answer, but I don't know actually what's happening there. Fantastic. Take a look at the stress strain curves, and let's actually look at the next problem, number 3 below. So for number 3, we're looking at specifically SR14, and the lattice resistance, so TLR, is going to be equal to our yield strength of SR14, which is our pink or purple curve, and let's just say that's around 2.5 MPa. Fantastic. So now we need to look at essentially this glide plane here that we can see. So if the angle is 45 degrees and sigma xx is 18 megapascals, what stress in the yy will be large enough to move this dislocation via dislocation glide? Is this stress large enough to create dislocations? If so, what types of dislocations? Okay, so this is my glide plane. So we have some stress, and we have a Burgers vector and a normal as well. So I've got some stress applied, and that stress is going to be in the sigma xx, sigma xy, sigma y, or sigma xy, excuse me, and sigma yy. We know that sigma, which one were we given? I think xx. Xx is 18 MPa. I see, and again, we're looking to try to figure out what is our Peach-Kohler force, or actually we're trying to find out our resolved shear stress, excuse me. So we need to find what is our resolved shear stress in this problem. So in order to do that, we're going to have to use our Schmidt resolution tensor. And that is going to require the following set of relationships. So we are going to say that our alpha is equal to 1/2 of Bj times Ni plus Bi times Nj. So, or vice versa. And our resolved shear stress will just be alpha ij, sigma ij. So we need to figure out what is our B and N vector. So we have this angle here. So if I resolve this and write B as a vector, it's going to be equal to cosine of theta, sine of theta, and then 0. And our N vector is just going to be equal to, so this is where hopefully we have our hopefully have our geometry ready ready and raring to go effectively here. So there's going to be minus sine of theta and then cosine of theta and then 0. So and we know that theta is equal to 45 degrees. So theta is equal to 45 degrees. So let's go ahead and let's start to solve this problem. So I'm going to do a new notebook. Actually, I'm going to use this. I'm going to use some of the values that we have in our exactly. So let's go ahead and let's just clear everything. Clear the whole kernel. Quit. So I have a sigma xx. So I have, this is 18 MPa. We have sigma xy, then we have 0. We have sigma xy, we don't know what this is, and then everything else is 0. 0, 0, 0. So that is my sigma. My B, and let's zoom out again. So nice, so nice. So let's go over here. my B, my B1, actually, let's just call it B now. My B is equal to cosine of 45 degree sine of 45 degree 0, and then I'm also going to have my N is going to be equal to, I'm just going to call this B, E, N is going to be equal to minus sine of 45 degree, and then cosine of 45 degree 0, 0 here, and there we go. So I've got my alpha now, found that alpha, and then I can go ahead and start to, once I have that alpha, to find my resolved shear stress, alpha times sigma, flatten, sum all those values. So I have got this relationship now as a function of sigma y. So this is my resolved shear stress. Again, one number. So the question is asking us what? Let's see. So we know that when our resolved shear stress is equal to or greater than lattice resistance, we're able to move those dislocations. So I can solve now. I could basically go like this. I could solve, when does this equal, I need to make it 2.5 times 10 to the 6. So this has to be my sig yy. So this would be the value to get there. Excellent. Let's see. That's new dislocation glide. Is the stress large enough to create dislocation? So again, once this is my resolved shear stress, now I could also use a different. So now we're asked the question, okay, are we able to essentially create or nucleate dislocations? So if we're nucleating these dislocations homogeneously, we have the following relationship, that my critical tau c is equal to GB over 2 pi L. So depending on what this material is, I know that my T sub c is equal to 2.5 MPa. So that's equal to my T sub c. So depending on my G, my Burgers vector, and my L, I can now find relationships for what size of dislocations I could actually nucleate. So actually I could solve that. So let's say Z equal to G times B Berg divided by 2 times pi times L. And let's solve that with respect to L in terms of all those other variables. And you can get those values. So again, depending on the material, these are the exact, essentially the length of dislocations that I could create. So there we go. That is pretty much it. So let's go ahead. Do we answer all the questions? Yes, we did. Fantastic. Now let's get on to number 4. After we do some, let's do some nice erasing here, although I'll probably regret it. Let's do some erasing. And then now let's get into number 4. So for number 4, we're looking at a thin-walled pressure vessel. So if I look at this coordinate system, actually we're not sure if we're thin-walled yet, but I have a sneaking suspicion we probably are. So let's go ahead and let's kind of set this problem up. Again, I'm going to quit the kernel, quit it. Then I'm going to look at, I am given a diameter, so a radius which is equal to 2.5 meters. I have a thickness. The T is going to be problematic, but thickness is 100 millimeters. So, and my del P is equal to 5 times 10 to the 6. It is metal, so my Young's modulus Y is equal to 100 times 10 to the 9th. My nu is equal to 0.4 or 0.3, excuse me. So let's do R over T. If it's greater than 10, we can get to our work. Fantastic. So I know that in my coordinate system here, my stress tensor for this problem, in my 2 direction is my longitudinal, in my basically my 3 direction around, that's going to be my hoop. Everything else will be 0. And we know the procedure from here, so hoop is equal to delta P R over T. sigma longitudinal is equal to delta P R over 2T. My epsilon H is equal to 1 over E times sig H minus nu sig L. And EL is equal to 1 over E times sig L minus nu sig H. We'll go over this in our notebook as well. So I have also a edge defect here that is I have a tangent vector which is in the basically 1, 0, 0 line direction going into and out of the board. And then I have a Burgers vector that's acting in that 2, 3 plane. So I could have it, my Burgers vector in the 3, or I could have it in the 0, 1, 0 direction. That would work. But let's kind of keep working throughout this problem. So I have my sig, which is equal to, like we just said, 0, 0, 0, 0, sig L. Actually, now we need to define sig H equals del P times R divided by T. Sig L equals sig H divided by 2. And so sig L 0, and then 0, 0, sig H. So that is my stress tensor. So I need to first calculate what is the PK force. So we know our description for our PK force. So let's go ahead and look back at that. So our PK force, we're going to do, we'll grab this guy. So again, I'm going to assume that is my Burgers vector direction. So let's go ahead and here, go here. So my FPK thin walled is going to be sig dot, again, where's my, let's actually, I thought I defined that previously. So let's go, actually, no, I didn't do it here. So let's zoom out a little bit. Let's go over here again. Let's bring it over here. So I'm going to say that my Burg is equal to 0, 1, 0. My T is going to be equal to, yeah, T vector 1, 0, 0. So my FPK thin is going to be my Burg, and then my TV cross. So I'm only going to have that stress in the 3 direction. So basically a climb force. What is the resolved shear stress? So now we're going to be using essentially our alpha. So remember, for our alpha, and I just erased it, and that's what I didn't want to do. But for, actually, here it is. For that alpha, we have that defined previously. So let's go ahead and let's grab, essentially, our alpha will be this. So we need to figure out, we have our Burgers vector, we need our normal. So my n, my normal, is going to be equal to my TV, actually cross TV Burg, and I need to divide that by my norm of this. That would be my unit vector. So again, same value there. So now I'm going to do, this is going to be my Burg, this is going to be my normal, and then Burg, normal. So that is my alpha, and then finally, to get my total, it'll just be this. So my resolved shear stress, let's go all the way, excuse me, here. For normal, up there, will be alpha sigma. So my resolved shear stress is a astounding 0. So there's nothing acting on that plane there. Is it large? Nope. 0, 0. That's it. All right, let's get on to, again, not exciting, but it is what it, the answer is what it is. You could play around and actually see what would the impact of changing this to, for example, like a -1 be. Or if you had it essentially in that 3 plane. But you see nothing happening here. I'd be interested to see what happens if you do it here. And we got this, still got this. This is something here. But yeah, nothing. There we go. All right, on to number 5. So I'm working with a cube of vanadium. And I see the stress state applied below. I have the Burgers vector here. And then let's start to work out this problem. All right, everyone, so let's go ahead and let's start Pset 6 solution videos. So let's take a look at the following schematic: edge dislocation. At the dislocations indicated, tell me whether vacancies or interstitials want to form at these locations. All right, so we know that when we're looking at essentially the formation of these point defects, so vacancies or interstitials, we have the following relationship that we could always kind of call upon. So if you remember previously in class, we said that the new enthalpy of formation, and let me write this. So the new enthalpy of formation of some, again, X just stands for vacancy or interstitial, will equal the regular enthalpy of formation of that defect plus P delta Vx. Again, the basically the change in volume at that point, whether it's a vacancy or interstitial. So we know that pressure is equal to minus 1/3 sigma 1,1 plus sigma 2,2 plus sigma 3,3. So if I look, so let's see, we have this edge dislocation here. So if I'm drawing my coordinate system as X and Y here, we know that at this dislocation, in this spot here, number 1, we are in compression. So our stress is negative, and here we are in tension, that is positive. And that, we could prove that looking at our fun little chart here. So these are our stresses. So if I look at the value, so doing my contour plot, reverse temperature mat. So again, the small values now will be, or actually the negative values will be in red, the positive values here will be in tension. We could look at this as like sig x. Look at sig xx slash dot x goes to 0. Let's go y goes to 1. Oops. Let's do this slash dot x goes to 0, y goes to 1. So we see negative values. So we are in compression at the top. So if I look at the change in volume of a vacancy, what happens when I remove a vacancy? That change in volume of a vacancy it's going to kind of basically relax back in. So that change in volume will be essentially, it is going to be negative. So this will be negative, and it'll be about 1/10 of our basically atomic volume. Change in vacancy for change in volume of an interstitial is going to be positive, and it's going to be on the order of atomic volume. So when I look at this term here, don't really care about this. This is the term I want. So where will interstitials or vacancies want to form? So let's look at vacancies first. So my vacancies have a negative change in volume. So if I'm looking at position 1 or position 2 here, so if I'm in position 1, my pressure values, these are all negative as well. So I've got a negative here, a negative here. So what's going to happen? Actually, let's go ahead and look at this here. So I've got negative values here, and then if I look at my pressure, which is equal to this negative here, so what is going to happen? So let's go ahead and let's start to kind of get this notebook set up. So I'm going to basically clear everything here. So we have a Burgers vector in the 1, 1, 1 direction, and in the 1, 0, 0 plane. So in the plane, so basically that is telling me that my normal, so my Burgers vector is equal to 1, 1, 1. I also have my, basically I know my normal is going to be equal to 1, 1, 0. So I have the following search list. Here we go. And then now, excellent. We think we're going to assume that we are working with, again, actually we have to assume because we're calculating Peach-Kohler forces and then resolve Shear as glide planes. So we're going to assume that we are working with an edge dislocation. So I need to basically solve for what is, or what could be, essentially that Burgers vector. Actually, let's go ahead and see. Actually, we don't have to make this assumption, I believe so. So actually we have to because of the PK force. But first, let's go ahead and actually look at what is the resolved shear stress. So I've got a stress in this system that is in MPa. Let's see, what do I have? I have a stress in the 2,2 that's 17. I have a stress in the 3,3 that's minus 55. And I also have, and it should be drawn on the other system, so normal's in the 2, so sigma 2,3, that is positive, and that is 78. 78. 2, 3, 2. This is actually the infamous one where students are cheating. So let's zoom out a little bit. So my sig, again, so my sig is equal to 0, 0, 0, 17, 78, 78, minus 55, times 10 to the 6, oops, no, times 10 to the 6, so that's my sig. My Burgers vector is such, my normal is this, so the normal is 1, 0, 0, so we can actually solve this now. So actually, what we can do is solve. So I need to figure out what is my x, y, and z. I need to cross. Actually, because I know my normal. My normal here, I'm just trying to find my tangent vector first because I'm going to need that for my Peach Kohler force. So I know that my normal is 1, 1, 1, 1, 0, and I don't know what my tangent vector is here, and I know what my Burgers vector here, b, that is 1, 1, 1, so I don't know what that tangent vector is. But hopefully we can solve for that, t, b, and then z, let's put that in here, z, and it does not like us solving this. Doing like that, doing like that. So we can actually start to try to make some assumptions, because you could also set the relationship. So we want a numerical solve. So we could also say this, that this is one expression. This must be equal to this. Honestly, we could probably, let's see if we can solve it first. Alright, so it still doesn't like that. Tangent vector. Even when we don't do that, set the numerical solving it. Nope. It's actually when we cross this, this and this. So let's keep working on this. So we could also assume that we're working with an edge defect, and that we're going to be doing basically b dot with our x, y, z must be equal to 0. And that's still giving us problems. So let's actually look at what some of these values could look like. So if we cross this here, let's give us some values. Very interesting. And then let's solve. What guys x, y, and z dot with b set equal to 0. So z must be equal to minus 1 and 2. So we could start to solve for this, but for the moment, let's go ahead. So we want to find, I have that Burgers vector in that plane, so now let's keep moving. Actually, let's just do resolve shear for stress. So the Peach Kohler force is not something that we could really calculate right now unless we know those values. So instead, what we will do, in fact, is start to work with different values. Actually, I'm going to try one more thing. I'm just a little bit interested. Let's do t equals minus 1, 1, 0. Because that will give us that. Let's do norm, actually cross of t and b. That's the problem there. If we do a t 1, 0, 0. Yeah, we're just switching those values. I'm just trying to look at, see if by inspection we could find a value. But again, we're still assuming something. So again, I wouldn't be comfortable with calculating the peach color force unless we actually knew what the dislocation was. Edge screw, and then again, we can't use the definition for those. So it may be a screw, so we can't calculate those values, so we don't know what they are. So, but we can calculate the resolved shear stress because I know my B, I know my N is equal to 1, 1, 0, as we've seen here. That is my N, that is the plane it's on. So my alpha is going to be B, N, B, N. Get those values here, sum those. Ooh, I need to clear my sig because my sig, actually let's see what my sig is. Actually, here's my sig. So we got those values and we've got our resolved shear stress. So that's the shear stress in the glide plane. And what dislocation lanes will occur? Well, we can actually start to estimate essentially vanadium. So in my vanadium, I know, and we have a relationship between G, again, if we assume as linear elastic isotropic material, I could relate my shear modulus to my Poisson's ratio and these other values. So hopefully we remember all the way back. So if we remember way back, to our linear elasticity lectures, we should remember that like epsilon, for example, epsilon 1, 2 is equal to, basically, I'm going to look at 1 plus nu sigma 1, 2 over E. So, essentially, if we were looking at gamma 1, 2, which is equal to basically twice this epsilon 1, 2 value, it would be equal to gamma 1, 2. We divide this out, and then we can write those values here. And we know that basically I could rewrite this in terms of my shear stress, tau 1, 2, forcing 1, 2, the same thing. It would just be 2, 1 plus nu over E. So my shear modulus G would be equal to E over 2, 1 plus nu. We know that E is equal to about 300 GPa for our ceramic, nu is equal to 0.2, and now we can go ahead and start to solve this problem. So now we can actually get an estimate for our G. So we have our critical or resolved shear stress, so let's go ahead and let's start to calculate this out. So let's say that G is going to be equal to, oops, so let's do G is equal to Young's modulus, which is 300 times 10 to the 9, divided by 2 plus 2 times 1 plus 0.2. Again, this is just generic value for ceramic. And then I could solve for, and again, let's go back. Actually, we can hopefully see our notes. Nope. But we should know from our notes what is the value for basically nucleating those shear stresses. Actually, we've just done it previously for another problem. So we should remember that in order to for enough stress in order to start to nucleate, and again, remember, we are always talking, we have our expression for homogeneous nucleation, but oftentimes, heterogeneous nucleation will be easier. So this is my critical resolved shear stress value, set that's equals to G times B, but our Berger's vector here, we could actually estimate this as 2 pi r. So we're assuming the smallest Berger's vector, so we're moving in the plane. Again, this is a little bit difficult because we really don't know what type of dislocation we're dealing with here, but let's go ahead and make a kind of a little bit of a simple assumption. So I'm just pulling up our good old-fashioned friend, our periodic table. Let's download that. Let's go look over here. Let's bring it up. Apologies, but this is always the fun part. So we are looking at what was our material. Let's go, oops. Actually, here I think we're. Oh, excuse me, vanadium. So we are not. My deep apologies. We're not dealing with the ceramic. We're dealing with the metal. So let's go ahead and correct that here. So vanadium. So 100 GPa here. Nu is going to be a value of 0.3. And vanadium, I believe, is a BCC metal. Apologies for that one. I was thinking we were working with tungsten. So if we look at vanadium here, yeah, BCC. What is our metallic radii? I believe it's 1.36 because our metallic radii should be the second value down there below. Yep, so 1.36 angstroms. So my nearest neighbor distance, assuming we're moving there, let's go ahead and change this. 100, 0.3, there we go. So 1.36 angstroms times 10 to the minus 10, minus 10 times 2, all divided by 2 times pi times L. So now you could solve for the lengths. So these are the lengths that we could, again, you could kind of strictly nucleate, because actually we could go ahead and pull out this equation. So let's see, slash dot L goes to, let's see, 1 times 10 to the minus 9. So this will be, actually, so we can't get those values if we do minus 5. So absolutely, we can nucleate that. We have enough stress, we can nucleate those values. So we can't go less than this value. Fantastic. All right, let's zoom back in and see which problem we're working with here. All right, so we've got that down. Stress, dislocations, which ones will create? We got it. Fantastic. So now let's go ahead and start to work on this other problem. So I'm going to go ahead and bring up that notebook again, defects. I'm going to clear the kernel, and let's go ahead and read it side by side. So we're asked to calculate the peak K forces for the following scenario. So edges and screws and all this good stuff. So let's go back to our, actually, let's go ahead and start, because we're looking at the forces of defects on one another. So I'm going to call this sig xx. So let's go ahead and define that here. And let's define essentially, this is my edge stress. So it's going to be this. So my edge stress state is going to be that value here. I'm going to do the same thing for my screw stress state. So there we go. All right, so we're going to calculate our Peach-Kohler forces. Let's go ahead and go down. Pretty pictures. Fantastic. All right, so if we remember, and we have our expression previously, so we're going to do stress, the stress acting on 1, B2, T2. So the general expression, if I have basically a force of 1 acting on 2, it's going to be equal to the stress of 1 acting on dot the Burgers vector cross the tangent vector of 2. So again, that's our general expression for what we're looking at here. So the stress that 1 is exerting on our 2 defect, which is defined by that Burgers vector and all those good values. So let's go ahead and let's get it started. So edge dislocation on edge dislocation. Both have tangent vectors aligned with the z. So here we go. I'm just going to call this in general T, in general B, and then we'll just give it a magnitude. So edge on edge, both have tangent vectors aligned with the z and Burgers vectors in the y direction. So I have basically 0, 0, comma 1, comma 0. So that is my, whoops. Oh, that's not good. B mag. Let's see if that'll be better. So let's go B. Let's cross it with T. So again, I'm looking at the stress. Again, I have this stress state is always for a line direction for either edge or screw aligned with the Z. So I can only use that if I have those values. So I could cross that. Oops. I think it doesn't like that I, let's see, what are my dimensions? Stress. What about my P? Mag. Should be okay. Let's see. What does it like? Do I have, what is edge stress? Let's look at it. I think I have an extra, yeah. There's a little extra something happening there. It should be okay. Why is it putting an extra parentheses on this? Have B that's described. Ah, I see. Okay, so the issue is that's why you don't, that's why I described it as B2. Let's start this over. Let's clear. And then let's, yeah, actually, let's go ahead. This is actually the problem of, make sure their notebook, making sure you're not assigning values that are defined elsewhere in your notebook. So we've got that. Let's get our edge stress as well. So again, we're just redefining this. We are adding, unfortunately, another, basically a vector within a vector. Let's try to find our, oops, apologies again for making you all dizzy. And then, all right, now let's get to B2, T2. Let's stick with, again, like don't have to look at those values now. Look at that. B2, T2, and voila. So I have some stress in the X direction, some stress in the Y direction as well. So those would be my key polar force, or peach color force. Fantastic. Edge dislocation, so still my edge stress on a right screw. So the edge dislocation has a tangent vector Z and a Burgers vector in the X, doesn't matter that, while the right screw has a tangent vector aligned in the Y direction. So if it's a right screw, I also know that it must be parallel, so I could calculate that. And you see I only have a stress component in the 3 or the Z direction. Excellent. Right hand screw on left hand screw. So now I'm going to change my stress to screw stress. So a right hand screw on a left hand screw. Right hand screw, tangent vector there. We know it must be in order to kind of write that stress state. The left hand screw has a tangent vector in the negative X direction. So that means I have, it's anti-parallel. So I must have this, this, and again, edge or screw on screw, we're not going to have that defect. Left hand screw on an edge dislocation. So left hand screw is tangent vector, again, still the same screw stress here, but now I'm dealing with an edge tangent vector in the negative Y. So negative Y, that's my tangent vector. Tangent vector in the negative Y, and a Burgers vector in the positive Z direction. So 0 here, and again, nothing going there. So that is it. Excellent. Now we get to our last but very important reactions here. So I have the following reactions for each in aluminum crystal. So we're FCC material. So we have these several reactions, and in the equation above, prove that the first reaction and all Burgers vectors are in the 1, 1, 1 plane. Prove this. Prove this is created. Is this reaction spontaneous? So let's look. All the vectors, all the Burgers vectors here are in the 1, 1, 1, 1 plane. Is the reaction spontaneous? So let's just see if it's spontaneous. We're going to apply Frank's rule, which means that I am going to assume that, or not assume, if the magnitude of the products is greater than, or actually is smaller than, if I do the sum, let's put it down here. My Frank's rule says my reaction spontaneous is the sum of the magnitudes of my Burgers vectors in the products is less than the sum of the B reactants, then I am some reactants. Let's just write that properly. This is the sum of the magnitudes B reactants. Then it is a spontaneous reaction. Why? Because we don't want to produce, we want less dislocations in our material ideally. So let's go ahead and let's break this down. So so let's just write down actually. So we need the norm. Norm is going to give me my magnitude. So basically A divided by 2, and then I got 1, 0, minus 1. So let's get that one going. And then we could do the same thing for norm of this plus, because we are left with then A over 6. Oops. A over 6, A over 6. We got 1, 1, minus 2, and we've got 2, minus 1, minus 1. So now we could set the question, this is my prod, or actually reactants. React equals this, my prod equals this. So prod less than react. Actually, we could actually do the question. But again, we actually can just see this. So let's look at those values. So my reactants, so let's square root 2 divided by 3. Let's look at that numerically. What is 1 divided by square root 2? So Is this reaction spontaneous? No. So again, looking at these values, the sum of the magnitudes of my products is greater than that of the reactants. So this is actually not going to be a spontaneous reaction. So nope, not spontaneous. Second equation, the first Burger's vector is contained in the 1, 1, 1 plane. The second is in the 1, 1, minus 1 plane. How can we prove this? So one of the ways is we can actually go ahead and you can actually see these Burger's vectors. Again, when we're looking at these reactions, we're always looking at edge defects. So we can actually see, so for example, these are my Burger's vector. I know that I have an equation for my tangent vector must be in this planes, but actually we could go ahead and prove this a little bit. What is the tangent vector for the product reaction? So we can actually go ahead, so first let's answer that first question. So how do we prove this? Well, we know that our normal is equal to tangent cross my Burger's vector, as such, tangent cross Burger's over magnitude tangent cross Burger's. So if I have my Burger's vector here, you can actually should go back and reprove that. But again, we're given that these are in this plane, and I can prove this. You can kind of show, given a tangent vector that works, you can satisfy this relationship. What is the tangent vector of the product reaction? So this is actually the key piece of information. We know that the normal, so for this first, I'm going to call this reactant 1, I'm going to call this reactant 2. The normal of 1 is going to be equal to basically the 1, 1, 1 direction, because that is the normal to the plane. Same thing for 2, 1, 1, minus 1. So I can now solve for the rest of those values. So if I want to look at the line of intersection of those two planes, I am going to do the cross product. So I'm going to call this, again, let's actually zoom out. Let's move it a little bit to the side. I think we can still see, hopefully. So when I look at my N1 is equal to 1, 1, 1. My N2 is equal to 1, 1, minus 1. Dot. Actually, you could kind of do this. So I could solve, for example, let's go ahead and set that N1 set equal to, let's see that my Burger's vector 1 is going to be equal to basically minus 1, 0, 1. It's going to be, I don't need the A over 2, I'm just going to look at directions. So for example, it's equal to cross of x, y, z, cross it with my B1, and then you can solve for that. And then you could also set the additional expression that, again, I need my basically x, y, z dot B1 by t cross b, I need to be 0 because that's 90 degrees for edge dislocations. So voila. So you can find essentially that tangent vector, so you can prove again. And if you do the normal again, this is all by definition. So my point is what we were searching for previously. So if I want to find the line of intersection, I'm going to cross N1, N2, and that is my tangent vector. So it's 2, again, if you normalize it, it is going to be this, my tangent vector that results here. So for this Burger's vector, for the product, my tangent vector, or basically the product, we call that 3. My tangent 3 is going to be equal to, what was that here? Minus 1, 1, 0. Minus 1, 1, 0. So I've got my tangent vector. I've got my Burger's vector here. Let's zoom in, 0, 0, 1. A over A times 0, 0, 1. So let's say my B3. So my T3 is equal to minus 1, comma 0, 0, oops, comma 0, comma 0. Minus 1, 1, comma 0. Yeah. And my B3 is equal to, let's see, my B3 is equal to 0, 0, 1. So now I can figure out, so now the question is, okay, I figure out the tangent vector. What is the slip system? So I've got my direction. My direction in my slip system, I need my plane that my that contains essentially my my Burgers vector, the result, the product. So my direction is the family of the 1, 0, 0 directions. Now the plane, I've got my tangent vector, I've got my tangent vector, I've got my Burgers vector. So now I can find my normal 3, which is equal to cross T3, B3, and that will be the 1, 1, 0 plane. What is my slip system for FCC? 1, 1, 1 and 1, 1, 0. So this is not a sessile reaction. So this will not occur. Fantastic. Further questions, same question, and the first 2 Burgers. So again, we could answer the same exact question, except now our T3 is going to be, we still have the same T3, our B3 has changed to become 1, 1, 0. So if I cross this now, so in this slip system for the third reaction here, my slip system is in the 1, 1, 0 direction. That's a good start. But where am I in my terms of my plane? I'm in my basically 1, 0, 0 plane. So again, this is not motile either. So neither of these are all going to be sessile. Finally, what about defect reaction BCC material, specifically the one below? So is this reaction spontaneous? So let's go ahead and let's check this one out. So I'm just going to call this, again, let's do our, except now we're going to do, this is going to be our react, this is going to be our prod. We're going to call this A1, 1, 0. This is going to be our reactant, which is going to be A over 2, and we're going to call this 1, 1, 1. We're going to call this 1, 1, minus 1. So reactants, so this is a spontaneous reaction. Fantastic. The students claim this comes from a motile slip system. Prove whether this is possible or not. So I'm looking at a defect in this, in this system. So I've got my Burgers vector. Now I need to see, again, what would be, I actually need some additional information here. See, because I don't have, I need to figure out what is my, actually I need this, I need some more, I need some more information. But let's go ahead and let's try to figure this out, because I need to know what's the plane that contains this vector, because this is my Burgers vector. So my Burgers vector is, basically, if I look at the directions, actually I can answer this right now. So my slip system for BCC is what? I need to be in the 1, 1, 0 plane, and I need to be in the 1, 1, 1 direction. So already, I am not going to be motile, because I see that reaction coming here. But let's kind of see, or actually, let's try to figure out what plane I may be in. So I can write, let's just, again, let's pick arbitrarily a tangent vector here that would work. So one tangent vector that will dot product that make this 0 would be, so for example, T1 could be, one of the things that would work is basically, I could look at minus 1, 0, 1. This would give me a dot product that gives me that value. So if I do that, if I write my T1, my B1 I know, which is 1, 1, 1. My T1 could be minus 1, 0, 1. And then my N1 equals cross of T1, B1. So that could be a normal to the plane. It's not a nice normal. I will say that. For example, I could do minus 1. Actually, I can't do that. I could do 0. I could do 0. Actually, can't do 0, 0, 0. Yeah, it has to be some combination of 0, minus 1, 1. So that will work. Again, that could be the normal. It's not a nice normal, but let's just say this is the normal that works. And actually, we could go ahead and we could do divided by the norm. That gives us something nasty, but again, if you want the unit vector. But let's just cross this, and let's say our T2 and B2, let's do this the exact same way. So not a nice value necessarily. So my B1 is 1, 1, minus 1, and then my T, I can get basically a 0, 1, 1. That would give me a dot product of T2, excuse me, 2, T2, back, N2, T2, T2. So I can now do cross, I get this right here, of N1, N2, and I could essentially get that value. So either way, we are not essentially in that slip system. So we are at something actually completely different. So, yep, that's essentially all we've got. So we can go ahead and actually move forward. But you know, basically, we're not going to be in this. The answer was already kind of killed out. We know that it's not motile looking at that direction right there. So fantastic. Again, this is essentially the way. Find the normals, create those values, and then you're good to go. Excellent. Thanks. I'll see you in the next video. Bye.